So the third presentation of this morning is by Thibault Reuille and Dhia Mahjoub. So without further ado, please go ahead.
Thank you very much. So hi everybody. Hi Virus Bulletin. Very pleased to be here. It's an honor to be invited at Virus Bulletin. It's the first time for us, especially first time in Seattle as well. Beautiful city. So the title of this presentation is Designed to Discover Security Analytics with a 3D Visualization Engine. Now allow me to quickly introduce myself. I'm Thibault Reuille. I'm a security researcher at OpenDNS, and the main focus of my research is data visualization. Before that, I used to be a software engineer at NVIDIA for like 4 years, and now I apply my data visualization technique and 3D graphics technique to pretty much the data that we're having every day at OpenDNS.
And then I'm Dhia Mahjoub, so some of you already saw me in a previous talk, and the focus of what I do is basically analyze our DNS data and IP infrastructure to discover new threats. Without further ado, the agenda of today will be as follows. So we'll start with a presentation of OpenDNS, and then we'll talk about our threat intelligence platform. We call it 3D SGraph or 3D Investigate. And then we'll talk about one of the models we have, the co-occurrences model, which is very useful to discover new attack domains. The way we explore this co-occurrences graph, because it's about a graph, as you'll see later, is to use a ripple effect phenomena, and we'll explain it. And then we'll showcase this model with two use cases, one about CryptoLocker and the other one about Zeus Game Over. And then we'll conclude with some interesting points. So the OpenDNS worldwide presence consists in 23 data centers across 4 continents. And that allows us to see a lot of traffic. It's of 2 types. So we have the recursive traffic, which is between our users and us, our resolvers. So for that, you'll see like timestamps, client IPs, and domains with some other features. And then on the other side, you have the authoritative traffic. And that's basically between our resolvers and the authoritative name servers of the internet. And that's how we basically build our DNS DB. So all of that data allowed us to build this threat intelligence platform. And as you see here, it's the web interface. So at the top, you can enter like a domain, an IP, or an ASN. In this case, it's www.virusbulletin.com. And then what we can see is the traffic or the lookups over the past 30 days from our users. And interestingly, you see that Virus Bulletin is a popular site because it's a periodic pattern with some spikes in some days. But overall, across all of the data centers, you see that people regularly go visit the site, you know, to get all kinds of information about the conference or about blogs and other info. The other thing you can see at the second part of the slide is that you have the requester geo-distribution, and that's basically a breakdown by countries that are looking up this domain. So again, you can see how popular a domain is across different geographical regions. The other part of this web page, and obviously you could use this via bulk API lookup, but what we see on the web interface is basically the IP address. So in this case, it's a CNAME, so it's an alias for another host name that has an IP. And we also can see the name server's IP. So since we see the authoritative traffic, then we have also visibility into all of the name server's IPs that respond to us with the records. And in case of DNS hijacking, you'll be able to figure out if there are some anomalies in the responses you're getting. And finally, at the bottom, you have the co-occurrences and related domains. And these are the kind of the topic of the talk, because we're talking about domains that have been looked up by the same people during a short time period. And in this case, we see that Virus Bulletin is popular also with AV-Test and Usenix. And these are security-related sites. So somewhat you can also find other related sites in terms of themes or campaigns or topics.
So, as Dhia just explained, the security graph is an amazing tool, to have a lot of indicators and pretty much see a mashup of all the information that we have extracted from our DNS logs. But I would like to give you a different perspective of the security graph. The first one, the web UI, is showing you one IP, one ASN, or one domain, and has a lot of information. But let's try to step back a little bit and look at several domain or IPs together. And this is what we obtain. So in this model, we have a graph, a 3D graph that we extracted from wikileaks.org. And as you can see, there's a certain color code. The white nodes are the domain names. The cyan, light blue nodes are the IP addresses. The yellow ones are like the who is information that we have. And the purple ones are the ASIN numbers. So we have pretty much different types of nodes inside this graph. And these are all the internet entities that we extract from our DNS logs. And also we have different type of edges. It makes complete sense. We have domain to IP mapping. So that's a relationship between domain and IP. We have domain to who is information. We know who registered the domain. We have different domain connected together that could be related domains or co-occurrences, the one that Dhia just explained. And you can see on some edges you have a small particle floating over them. We mapped the speed of that particle on what we call the co-occurrence score. We're going to describe it a little bit later, but essentially it's, in summary, it's pretty much looking at traffic and the amount of traffic. Now, as you can see, the security graph is a graph. So we'd like to cover a couple of fundamentals before we go deeper into details. So a graph, in essence, is a set of nodes and a set of edges. It's also called vertices. So as you can see on this example, 0, 1, 2, 3 represents the nodes. And all the edges, 0 is connected to 1, 0 is connected to 2, etc., etc. That gives you a representation. The visual image that you have here is pretty much a representation of the formal definition of the graph. Now, obviously, graph theory is much more complicated than that. And, we pretty much build graphs that have different types of nodes, different type of edges, and we do a lot of things with them. Some metrics, just so you have an idea of the size of the graph we're dealing with. So it's a semantic graph based on our DNS logs. We have around 60 million DNS requests per day. And that gives us, after refining the information, like around 46 million nodes per day. That only includes domain and IP. And after that, 174 million edges per day. And that's also domain IP mapping. So dealing with a graph that size gives us a really interesting challenges. Especially in terms of data visualization. And we can pretty much summarize all the different approaches, with this triangle. The first one would be the grouping technique. This is how we can deal with big data. Grouping is pretty much looking at the high-level view of the security graph. For example, if you take the graph of all the employees in the company, while grouping would be grouping the employees by teams, and you can still see the hierarchy, even though you lose some granularity. Sampling would be just looking at a certain neighborhood with finer details, but like completely discarding the rest. So for example, that would be looking at me, my manager, my colleagues, and people under me. And parallelization, when all hope is lost to refine, like filter out the information, you just use more power to process the information. Now let's take a look at a very interesting first use case.
So our first use case will be CryptoLocker, and then we'll explain how we can use the model to explore the domains related to it. So all of you know about CryptoLocker. It came on the threat surface back in November or last fall. And then in a nutshell, it's a ransomware where if you get infected, then it will try to communicate with DGAs. And if one of them resolves, then it will download a public key. And then that public key is used in a process that will encrypt the files on your disk. And then you have a splash screen that will ask you to pay the ransom, otherwise all your data will never get recovered. Now the thing is, we use the co-occurrences model to track down these domains. So you don't have to necessarily have the sample to grab the algorithm or to observe what the lookups are looking like. What we do here is we use our logs, the query logs, so we have the timestamp, client IP, and then domain, and then we use the temporal proximity of domain lookups. And for that, you build a bipartite graph between client IPs looking up domains during a short time period. And from that graph, you'll build another one where you basically build an edge between two domains if they have been looked up by the same clients during that short time period. So let's say, as earlier we saw, virus bulletin was co-occurring with, let's say, usenix.com.org or with AV-Test or some other AV vendor. And that's because a lot of people went to visit Virus Bulletin's website, but they were also interested in visiting other security conference sites and related things. So that allows us to kind of study interesting use cases. So the first one that we mentioned is the botnet CNC. So in the case of DGAs, if you have malware that is looking up domains in succession with a high kind of repetitively, then you'll see it in the logs. And that way you can build those edges between the co-occurring domains. The other case was very interesting because, for instance, as an example, last fall, when the target breach happened, we saw a spike to a lot of carding sites selling stolen credit card information. So we started with the seed of these domains, and then we explored the co-occurrences graph, and we were able to grab a lot of other related carding sites, but also some hacking forums and sites that are related to the underground market, I would say. The other interesting case is when you deal with click fraud. So we have a lot of infected machines trying to connect to all of these sites and trying to generate fake clicks. So you'll see that in the logs. And using the co-occurrences model, you can also tie them together without even having infected machines with a sample and trying to dissect it on a host. So that's kind of the power here of the model. Now, the way we explore this co-occurrences graph is pretty simple. We call it the ripple effect, just for like a nice name, but it's basically a BFS that goes from a seed of domains, and then it goes either multiple levels or it just stops after a number of visited domains.
Now let's take a look at a visual representation of what a BFS and different sampling techniques mean. So on the left side, you have a representation of the BFS. I start with number 0, which is my seed domain. And then I traverse or explore the first ripple, the number 1, then number 2. So essentially, I take a node, the neighbors, neighbor of the neighbors, neighbors of neighbors and neighbors, etc., on different levels. This sampling technique has some defects, and we're going to explain them a little bit later. But let's consider this new one. The random walk technique is also very interesting. We start from one known domain, and then we choose a random path inside the huge graph that we have to deal with. So essentially, this random walk is going to be 10 steps, as you can see here. Start from the root and then choose a completely random direction. And I do that a couple of times. And the result is pretty much a sum of all the random paths inside this huge graphs. That can give you, even if you discard a lot of information, you can see deeper in the neighborhood, and you can see pretty much the structure of your cluster, the structure of everything that's around you. So let's apply that to a CryptoLocker and see how it looks like. So here in this graph, this is a co-occurrence graph. And we have a color code. All the red nodes are the known DGA domains. All the green ones are completely benign domains, have nothing to do with CryptoLocker. And all the white ones are the ones which we haven't classified yet. We don't know anything about them. So it's very interesting to see that just looking at those co-occurrences using the ripple effect, this BFS, and extracting all the neighboring co-occurrences, we can discover clusters, new clusters of DGA domains. Also, one thing that is important to notice here is that we have this pretty much green cluster here that's connected to those red ones. But if you remember at the beginning of the presentation, we talked about the co-occurrence score, which is pretty much the amount of traffic, transitional traffic. You can see that between the red and green cluster, you have a very slow particle, which means we have very few traffic. This is pretty much noise. So if you do an interesting analogy between extracting the DGA domains and extracting the brain tumor, that would be pretty much having a certain co-occurrence threshold and cutting the edges just to extract the right cluster. Now let's see how the random walk works on those data sets. Here's the same technique. We start with one known DGA domain. That wasn't the same day, but it's the same botnet. So you can see that the random walk chooses random paths in completely different directions. And what's really interesting in this data set is even though we didn't know anything about the structure or the topology of the cluster, we can still see this chain of DGAs. And also the color code here is a map on the DGA score. So if it's completely mapped on the red gradient. So if it's really red, it means that it's very likely to be a DGA. So again, you can see also some edges or some paths that are completely going in the middle of nowhere, which pretty much means they don't really belong to the neighboring cluster. So even though you don't know anything about the neighboring topology, you can still discover it using random walk techniques.
So as a second use case in this presentation is the Zeus game over. So Zeus Game Over, as you all know, is a Trojan, a banking Trojan, and there are like two versions that we know of. The old gauze that has been taken down or attempted to be taken down by Operation Tovar back in May, and the second version appeared back in July. And the first one was using peer-to-peer with the DGA fallback. The second one gave up on the peer-to-peer, but it used fast flux for hosting the CNCs in the beginning, but now they're kind of isolated IPs. But it still uses the DGAs for the domains. And we still see both old gauze and new gauze in our traffic, which is part of what we will cover here. So if we take old gauze domains, interestingly, for the domains of the day, we'll see them reappear for the next 4 days. And at the bottom, the co-occurrences data there is basically all of the domains that have been looked up during the short time period by the same client. So again, as we mentioned earlier, without necessarily having the sample, you can grab all of the domains that have been looked up by infected hosts. Just for reference, the MD5 for the old gauze is the one there you see. And then the behavior is that you have 1,000 DGA domains looked up by the sample before it stops, and then it will try again for the next few days. However, if you look at the new gauze, which we said appeared in early July of this year, the traffic is only for 24 hours, which is kind of the expected behavior. And we also see that the co-occurrences or related domains also show us the related ones that have been looked up by the victims. Now, the MD5 is that one for your reference, and the expected behavior was to have 1,000 DGAs looked up by the sample before it stops, and then it will kind of redo the process 24 hours before it goes to the next sequence of domains. Now, we were interested in seeing, just from our traffic, the kind of victims we have, or infected, potentially infected IPs. So for the old gauze, the concentration is still in the United States, but mostly Turkey, India, Indonesia, Egypt, and some African countries. And then for the new gauze, there's a lot of traffic coming from the UK and the United States, and some from India. And then we were interested in looking at the intersection. In other words, the overlap. So for that, we studied the domains of old gauze for those 4 days, because the list will kind of repeat for the next 4 days. However, for the new gauze, we took the domains generated for September 8th, September 9th, 10th, and 11th. And then we looked at the client IPs, looking them up, and then we tried to see the intersection. And we saw that the most infected countries were the United States and India, and then some in African countries and the United Kingdom.
Now again, let's take a look at this co-occurrence graph. We start from one known Zeus Game Over domain, and then we extract all the neighbors, neighbors, and neighbors, etc., etc. We can see that the accumulation of all the transitions between the DGA domains over 4 days creates a very dense cluster, as you can see here. And now I want to talk about one of the defects of the BFS. If you remember correctly, the BFS stops after a certain number of levels. The last level doesn't have any neighbors, which means it's going to be very sparse at the outskirts, at the edges of the graph. So this is something to consider here. So what you're seeing here is like all the traffic and all the transitions between all the DGA domains, and it creates something very dense. Now let's compare it. This is the old Zeus Game Over, by the way. Now let's compare it to the new one. So here's how we actually create a 3D representation of the graph. We start with all the points placed in the center, and like in kind of a sphere, and we use some particle physics. It's very simple. All the nodes that are connected are going to attract each other. All the nodes that are disconnected are going to repulse each other. And then we let the physics run, and we obtain kind of this molecular shape layout. It makes complete sense because the force-directed algorithm or model has been inspired by celestial bodies' forces. It's not exactly the same model because it's too complicated to implement, but it's very inspired by that. And then you can see the new structure, the topology of all the co-occurrences. You can see that it has a complete chain, and it's like it's looping at some point as well. Now, how did we create this data set? We used what we call the miner script. The miner script is pretty much a Python script that is going to do this BFS for us. It uses our security graph API, where we can request pretty much all the co-occurrences starting from one domain. And then finally, one thing that is really interesting to notice is the strict structure and strict topology of this graph. Almost every node in this graph have like around 10 neighbors. And the really interesting thing here is that since the topology is so strict, we can detect it automatically with our Python scripts. So we can pretty much extract things that respect the same topology without knowing what it is. Very interesting data set.
Less than 10 minutes, please.
So in conclusion, what we shared with you was an overview of our threat intelligence platform. So it's a product we have, but it's also open for researchers if you are doing your own research. So you're welcome to contact us to get access to it. We also introduced the co-occurrences model, which helps us build this graph that you can then explore, and then you'll find all kinds of domains that are either related to a same attack or they are related to kind of a theme that users are interested in. So we mentioned the carding sites. Also, we use it a lot to, explore hacking-related websites, sometimes click fraud, spam, everything where you have a lot of clients looking up domains en masse. That phenomena we can detect pretty easily with our models. The other thing we mentioned is that we have a unique view when we render this with the 3D visualization engine, because visualization here can be very useful in the sense if you just see the text or representation of nodes and edges in a textual format, you cannot see certain obvious patterns. But when you visualize it, you'll realize, like you saw in the Zeus came over case, it's a chain where every domain has a limited number of domains that are co-occurring with it over time. So this is kind of very interesting here. And like as Thibault mentioned, if you apply like some graph exploration on, if you're looking for certain patterns, like you're looking for specific subgraphs with certain features in your big one, then you can find islands of these suspicious related domains. And finally, the use cases that we discussed were CryptoLocker and Zeus came over, but we see it a lot in other DGA DGA malware, DGA-based malware. So I remember there were cases of SafeNet, RamNet, a lot of the known ones like PushDo, for instance, that uses DGA. So this can be applied in a lot of interesting threats. So thank you all for being here. We'll be very happy to answer questions, but also I would like to give a shout out to our research team. So Ping used to work with us, but then she left, so we miss her a lot. But then also Frank Denis and Anthony Kaza and Thomas and Andrew Hay. So thank you, everyone.